Now, I take this opportunity to share the documentation about Brilliant Group of Technical Institutions. Brilliant touched new heights under the able guidance of Dynamic Secretary of Brilliant Group of Institutions, Sri Kashireddy Narayan Reddy Garu, Honorable MLA Kalvakurti. His sagacious outlook and deep insight into the future needs of education won him laurels in India and abroad. He is honored with many awards like Vikas Ratan Gold Award by International Integration and Growth Society, New Delhi, and the Best Young Educationist Excellence Award by Cultural Association of Osmania University, Hyderabad. He established brilliant group of technical institutions after he had felt a gap between the engineering graduates and their industry readiness in terms of transformation of knowledge into practical application. His aim is to provide education on par with the international standards to produce world-class professionals. Brilliant Group of Technical Institutions was established in 2008 with the approval of All India Council for Technical Education, New Delhi, and affiliated to Jawaharlal Nehru Technological University, Hyderabad, Telangana, India. On a vast expanse of 70 acres campus near Ramoji Film City, free from noise and dust pollution, it has been a constant endeavor of Brilliant to incorporate great features of excellence in its campus. At a point when the industry is trying for a clear-cut distinction between quality and qualified in the professional perspective, a visionary, Sri Kashireddy Narayan Reddy Garu, realized his rationale to fill the gap between theory and application in the education of teaming millions of tech graduates so that they change the face of the globe. The mission behind the BCTI is to educate the students so that they become enlightened and transform to excel in their respective fields. First and foremost, with great respect, I take the privilege of inviting our Honorable Vice Chairman, Kashireddy Durga Prasad Reddy Garu, a true guiding force and constant source of inspiration. I request you, sir, to address this gathering and grace the occasion with your valuable words. Sir, we kindly request you to share your thoughts with us.
Sure. Thank you so much. And yeah, it gives me immense pleasure to welcome you all to this faculty development program on VLSI, designed for signal processing and communication systems, a field that continues to be at the forefront of innovation in electronics and semiconductor technology. At the outset, I would like to extend a warm welcome to our distinguished resource people, esteemed faculty members, and participants from various institutions across the nation. Your presence here reflects a shared commitment to academic growth, excellence, and continuous professional growth. And I'd also like to thank the ATAL Academy for giving us this opportunity and selecting Brilliant Institute of Engineering and Technology to conduct this amazing faculty development program. In today's rapidly evolving technological landscape, VLSI plays a pivotal role, whether it's in smartphones, artificial intelligence, IoT devices, or space technology. The integration of billions and even trillions of transistors into a single chip is not just a marvel of engineering. It is a critical enabler of progress across multiple domains such as 5G networks, multimedia systems, satellite communications, medical imaging, and real-time data processing. As an engineering college, we believe in empowering our faculty to become not just teachers, but torchbearers of innovation and excellence. Through initiatives like this, we are investing in the future of education and in the quality of engineers we will be sending into the world. I would also like to appreciate the Department of Electronics and Communication Engineering in Brilliant Institute of Engineering and Technology, along with all the organizers for their initiative and dedication in conducting this program. I encourage all participants to actively engage, ask questions, and make the most out of this learning experience. Let us use this FDP as a platform for collaboration, innovation, and inspiration. Together, let us continue to nurture an ecosystem where both faculty and students can thrive in the ever-evolving world of technology. Once again, I welcome you all and I wish the program great success. Thank you so much.
Thank you so much for your presence, sir. Now, I'm delighted to invite our respected principal, Dr. Sheikh Rustam Garu, whose vision and leadership uplift our institution to greater heights. We request you, sir, to deliver the presidential address and motivate us with your encouraging words.
Good evening and welcome to today's advanced faculty program, which is sponsored by ACT under the ATAL Academy. I welcome today's our Honorable Chairman, Kasiri Narayan Garu, MLA Karapurti, and Vice Chairman Kasiri Prasad Garu, coordinators Dr. R.P. Naraya, Dr. D. Kavita Madam, and our resource persons, media, EC department faculty, technical team of BRIL for supporting the program, and last and least of my colleagues, research scholars, professors, and participants, and media. The emerging trends in VLSI, design for signal process and communication applications, are transforming the industry. Key trends include AI and ML integration, design optimization, data-driven solutions, ML technology, techniques enhance signal processing tasks like anomaly detection and improve position, navigation, and timing system. Advanced hardware and integration like 3D integration, stacking multiple circuitry layers, increase integration density, enabling more complex and powerful chips. Novel materials, new semiconductor materials improve chip performance and efficiency, crucial for 2nm process nodes, dynamic power management, advanced systems, manage power consumption dynamically to meet complex application demands, and architecture and computing paradigms, edge computing, detected architecture, efficient performance, low power design, higher integration density, VLS process enable integrating billions of transistors onto a single chip. And wireless communications, VLSI design plays a crucial role in developing wireless infrastructure and devices, signal processing, VLSI architecture for signal processing, enable efficient data processing and analysis. IoT and real-time applications, edge computing, and low power design enable efficient data processing and literacy. This type of programs, thanks personally to ACT for encouraging and sponsoring this type of FD on different themes and combination of themes to share the knowledge throughout the India from different colleges. I thanks to the once again all the team of the supporting team of the EC department and technical team, media, especially our management, our dynamic vice chairman, continuously encouraging to organize this type of programs. Once he came here, continue supporting the programs. Thanks and one and all. Thank you. Thank you.
Finally, I take this opportunity to invite our respected head of the department, Vinod Garu, whose constant encouragement and support are invaluable to all of us. Sir, may I request you to share your thoughts with us?
Can you hear me?
Yes, sir.
Are you able to get my voice?
Yes.
Yes. Thank you.
Good evening to respected dignitaries. I'm Vinod, head of the department, EC, Brilliant Institute of Engineering and Technology. It's my immense pleasure to welcome you all to this faculty development program on VLSI design for signal processing and communication systems. On behalf of the Department of EC from Brilliant Institute of Engineering and Technology, I extend a warm welcome to our esteemed speakers, participants, and organizing team. As we all know, the field of VLSI design has become pivotal in shaping modern electronics with its applications spanning across critical domains such as high-speed communication, signal processing, and embedded systems. The convergence of VLSI technology with signal processing and communication systems is not just timely, but essential in driving forward the innovation we see in today's digital world. Whatnot, from 5G networks to IoT device, and in today's case, AI systems are built across these VLSI chips. This FDP is specially designed to provide a platform for faculty members to deepen their understanding of core VLSI concepts, learn about the latest tools and techniques, and explore real-world applications in signal processing and communication. The knowledge and skills gained here will not only enrich individual teaching and research capabilities, but also elevate the academic ecosystem of our respective institutions. We are honored to have with us a distinguished panel of experts and resource persons from both academia and industry, whose insights will be invaluable in brightening the gap between theory and practical implementation. I would also like to acknowledge and appreciate the coordinator of this FDP program, Dr. R.P. Naraya, and the co-coordinator, Dr. Kavita Madam, for their continuous effort in making this program a reality. Let us take advantage of this opportunity to collaborate, learn, and grow together. I encourage each one of you to ask questions and engage in discussion throughout the session. I hope the knowledge gained here will be translated to student community across the nation. Once again, I heartily welcome and I wish you all a productive and enlightening week ahead. Thank you very much.
Thank you so much, sir. Now, I would like to invite our program coordinator, Dr. R.P. Naraya Garu from Usmania University. So we would like to ask you to extend greetings and enlighten us with the objectives of this program.
Excuse me, sir, the voice is not clear.
So can you hear me now?
Perfect, sir. Now.
Good evening to everyone. So greetings from Department of Electronics and Communication Engineering, Brilliant Institute of Engineering and Technology. It gives me immense pleasure to welcome you all to the AACT ATAL online sponsored Advanced Faculty Development Program on Emerging Trends in VLSI Design for Signal Processing and Communication Systems, scheduled from 25th to 30th August 2025. At the outset, I extend my warm greetings to our respected Vice Chairman, Durga Prasad Reddy Garu, Principal Sheikh Rustum Garu, Head of the Department, Vinod Kumar Garu, distinguished resource persons from DRDO, ISRO, NRSC, eminent universities, industry experts, and all the participants who have joined us from across the country. We are happy to share that a total of 170 participants from various institutions, universities, industries across the country have registered. This FDP is designed with a vision to enhance the knowledge and skills of faculty, researchers, industry professionals in cutting-edge domains of VLSI, signal processing, and communication systems. Over the next 6 days, you will be engaged with the experts on the wide spectrum of topics from FPGA-based DSP design, signal integrity, wireless communication, GNSS processing, AI-driven innovations, to ethical practices in emerging. We believe that this FDP will not only strengthen your teaching and research abilities, but also open avenues for interdisciplinary collaborations. So I sincerely thank AACT ATAL Academy for their continuous support in promoting the quality faculty development programs. So here are some instructions for the participants. Before we begin, I would like to share some of the important points to ensure that the smooth conduct of this online FDP. The sessions links will be shared in the advance through the WhatsApp group and email and also WebEx link. So kindly join at least 5 minutes before the session starts to avoid the delays. Attendance will be taken twice through the Google Forms. The attendance form link will be shared in the middle of the session. Please fill it promptly, and this is mandatory for receiving the FDP certificates. So a session-wise feedback form will be shared after every session. At the end of the FDP, a consolidated feedback form will be also be provided. We will request you cooperatively in giving timely and genuine feedback, which will help us improving future programs. As per AACT ATAL guidelines, a test will be conducted at the end of the program. Participants are requested to maintain a minimum 80% of attendance and 70% marks in the test to be eligible for certification. For any doubts, queries, or technical issues, you may contact the coordinators through WhatsApp or email. We will be happy to assist you. Once again, I welcome you and look forward to highly interactive, insightful, and enriched FDP. Let us begin this journey of knowledge sharing and innovation together. Thank you, one and all.
Thank you so much, sir. A guest is not just a visitor, but a story of inspiration and success. Welcome our esteemed speaker to address us. Let us listen to his journey. We are honored to introduce Mr. Pradeep Kumar Woodla, Scientist F at the Defense Research and Development Organization. Pradeep sir holds a BE in Electronics and Communication Engineering from Osmania University and a master's degree in aerospace engineering from the Indian Institute of Sciences, Bangalore. With more than 18 years of distinguished experience, SAR has contributed extensively in the years of mathematical modeling and simulation of aerospace systems, configuration design, mission planning and guidance, and control of aerospace vehicles. His expertise and dedicated service have played a vital role in advancing India's indigenous aerospace programs. And it is a privilege to have him with us today to share his valuable knowledge and insights. Now, it's time to hear our great personality, who is the speaker of the event, Mr. Pradeep Kumar Vudla. We welcome you, sir, on behalf of brilliant group of technical institutions.
Thank you, madam. Thank you very much for the introduction. And it feels happy from my side to see such a congregation of academia and the practitioners like us. This is the first time for me, but this is what is expected, and this is what has to happen in India frequently. What I feel is going to the step. I take the slides for the topic. Just check whether it is shared properly and whether the voice is okay or not. Loud and clear, sir?
Yes, sir. It is
Yes, sir. Yes, sir. Okay. Okay. Proceed, sir.
Yeah. Sir, actually, I am into the missile control system design. Before going into the missile directly control system design, a brief and some small mathematical things to make you have a feel of actual what design happens in missile system. I'll walk you through all those things step by step and introduce you to missile control system and the components that are related to missile control system. You may please ask me wherever if the voice is not clear. Kindly, please. Sir, about the base, before starting the basics of missile system, is the slide shared clear to you, sir? Across all?
Yes, sir. Yes, sir. Yes, sir.
Yes, sir.
Right. Thank you. Let us start with a system, basic system. These need not be the standard definitions, but acceptable, understandable to make you have a feel of what exactly a system is. It is just an interconnection of components to perform specified tasks. And the components of any given system, it may be a Xerox machine, it can be a fan, it can be a missile or a cycle which we ride. The components are connected together by cause and effect relation. So every system has got input. Next, why do we have to design a control system for a system already existing? It so happens that the system could be unstable. Sir, I'm not getting the voice here. Is there anyone interrupting?
No, your voice is clear, sir.
Right. Sir, the basic objective of design of control system goes in these lines, sir. If the system is unstable, to stabilize the system, or the response times of the systems are not up to the mark, not up to the requirement, or system has got parametric variations and the response of the system is very sensitive to the parametric variations. In the field of control system, we came across these three terms invariably: dynamics, stability, and control. When we say dynamics, it involves the mathematical modeling of a given system, understanding it, checking the stability is checking the stability, whether the system existing, which is already mathematical modeled via dynamics, understanding the governing dynamics of the system, then study it mathematically using mathematical model, and then comment on the stability of the system. Then we can see whether the system is stable or not. If not, it's our onus to design a control system to stabilize it. And stabilization in the subsequent slides I will expand. And control of the variable. System has to be stabilized and specific variables are to be controlled because we want them to behave the way we want. So the control comes in that aspect. So as a control engineer, we live in this three-dimensional space: dynamic, stability, and control. The standard closed loop structure, negative feedback control system, which we are seeing here, starts with plant. For me, the plant is missile. As a missile scientist, the plant is missile, and the closed loop structure is like this. We want the missile to behave in a particular way. Sir, is the voice clear? Or
Yes, sir. It's clear, sir. Proceed, sir.
again? So we want the missile to behave in a particular fashion. What we have in hand is a reference input, and we want the missile to behave the way we want. And for that, we design a loop structure like this. Typically, any control system looks like this, which involves sensors to check the state of the plant and the actuators to implement the control law actual physical manner. And there are two inputs like this, two kinds of disturbance inputs, which I would like to emphasize because I started with dynamics. In the previous slide, I started with the dynamics of the plant. No tool or no way we can completely represent the dynamics plant, and it is perfect replication of 100% behavior of a plant is not possible. So any modeling errors that are not captured in the governed dynamic that affect us in terms of modeling disturbance, and the approximations that we do while designing the control system for a given plant affect us in terms of modeling disturbances, D1. The other disturbance which we are showing, D2, is typically a sensor noise. It can be of any form. We need to understand it and to handle it. And here is the controller. As we have studied some PID controller in our BE level, it still stands good. It still works in missile system. That's the way we handle the missiles. That controller sits here. As a control engineer, I'm the designer of this controller and the configuration of all the loop. And the specification of control systems come in terms of speed, the response times, the rise time, the settling time, the stability in terms of gain margin, phase margin, and things like that. Accuracy, that means accuracy majorly depends on accuracy of the sensor and the steady state response of the control loop design. And the disturbance rejection. There are disturbances which I have already meeting the accuracy. That's the way disturbance also comes as specification. Some basics before moving into the actual design philosophies, what we do for missiles, whether the system is linear or non-linear. If any system that follows superposition and homogeneity, as we all know, is a linear system. But as a control engineer, the day starts like this. No system is linear. All that we need to do is linearize the system if we have to use linear control system design philosophies, because linear control system design philosophies are well established, and the philosophy of linear system is easy to understand, easy to test, easy to implement, things like that. Because of so many benefits that we still go by the linear approach. Wherever we see non-linear systems, we try to linearize them. And the main tool of linearization is that comes to be Taylor series. Taylor series gives us although these definitions are well written in the textbooks, I'm not going through all those things. I want to make you have a feel of what exactly happens, what functions do we see in missile industry, and how do we handle it. That's my part of handling the course like this. The Taylor series basically gives the structure of a function, how the functional value and the derivatives are governing the functional value, the instantaneous functional value. Now, if we have, if we take care that x is so close by to c, x is so close by to c, in the expansion, the higher order terms go to 0. They become negligible. This is the way we linearize the system in aerodynamic. We linearize the system and use linear control system design philosophies. Not just that, although we are introduced to single loop control systems at our Bachelor of Engineering level, it is rare that we use single loop control systems. We go with, sir, are the slides clear and the voice is clear, sir?
Clear, sir. It is smooth.
Right. So apart from linearization, I want to make you have a feel of the functional behavior. The functional behavior is depending on its derivatives also. What we are seeing is derivatives also. So in order to control a signal, if we could control the derivatives also, the shape of the signal becomes very well. So this motivates us to use multi-loop control systems when we have to when we are expecting a perfect control of the expected control variable. Going into the next level, the time variant or time invariant. The definitions are very known to you. And what our thing is, for a given missile system, missile mass changes as it flies. There is a propulsion system that is accelerating the vehicle to higher velocity, and the vehicle is flying with a particular it does obtain the aerodynamics and so on. So the aerodynamic plant happens to be time variant system, and while designing a control system for a missile, we time slice the plant and extract the transfer functions and go for the design of the control system. Control system, I'm going back to the very first slide. This particular box, we are referring that PID controllers, those compensators which we had, and we have which we academically learned at BE level, and now we are applying them here. Going into the next level, the dynamical systems we face, it is ubiquitous that everywhere we face dynamical system. Sir,
Sir, it is clear, sir.
okay.
Yeah, audible and clear.
Right. Thank you. Thank you for the update. The dynamical systems are ubiquitous. What we mean by dynamical system, when we are mathematically modeling energy storing elements like capacitors, inductors, if it comes to mechanical things, stiffness and inertia, we call them dynamical systems. And as we know, as electronics and communication engineers, wherever there is a storage of energy, there comes some differential equations. So dynamical systems are characterized by differential equations. When we mathematically model them, we see that there are they are represented by differential equations. As a small example, just rehashing our basics. If a differential equation is found by linear combination of function and its derivatives, it's a linear differential equation. And if that linear combination has got a variable that is independent variable, it is a variable variant system. That means here it is time variant system. But if it is not a linear combination, that means function is formed by the function is in multiplicative form. Function is multiplied by its own derivative. So these kinds of systems are referred to as nonlinear systems. So just having a brush up of our higher engineering mathematics Just I'm taking you through those things. And before that, wherever we are seeing differential equation, this is the plant. This is a plant. And this is the forcing function. Forcing function is a function that is in our hand. We can control the plant by actuating this by proper modification of this forcing function. This design of this forcing function is nothing but design of control a linear differential equation it is. When we express the response of it, it has got two parts of it, transient response and the steady state response. And the transient response, if we see, it is characterized by the root of the auxiliary polynomial in here. Everything I am showing here in the time domain. Let us appreciate the first thing in time domain, then frequency domain, then the transfer function and things like that. First, let us understand the things very first level, what happens in the time domain. So this transient response is mainly characterized by the property of the system, that is sigma naught. And before going on to the stability of the system, it is just a linear systems are so simple that the response is also linear combination of transient response and steady state response. Since this simple addition, simple scaling is easy to design, easy to test, easy to evaluate, people still go by the linear control system philosophies. They impart, anyways, 90% of control they impart good results. Similarly, I'm taking you through a second order differential equation. When we see based on the nature of roots, we have transient response and steady state responses like that. No deal. The saying is the same thing. This is a part of the transient response. It is still depending on the property of the system. Now, whether the system is stable or not, as long as the transient response, we go to steady state response. It is expected. If the system is not, if the system is stable, this fellow is just an interpollant function. This fellow will die and the steady state response will prevail. It may be a unit step function, it is a ramp, or any signal, any practicable signal that is given as an input to the system. But if the system is unstable, if these roots are positive, these roots of these differential equations have positive real parts, this will bounce. This is no longer an interpollant between existing state and the future state. It is not an interpollant. It would be predominant over the steady state response, and hence we see the wrath of the unstable systems. The philosophy is the same. Whatever the differential equation, all things are linear differential equations. I am covering the whole class in linear domain only now. Now the stability. Before going to in details of stability, first we have to understand that where do we face problems of stability. Wherever that there is some implicit nature. For example, if we go to this differential equation, the implicit nature is the function is function of itself. If we place this component this side and see that y is the response of the system and the future response of the system is depending on itself. I am marking the thing. It is future of the response is depending on itself. This is making the system implicit. This implicit nature in a signal flow graph, we see it as a loop. Wherever there is a loop formed, it may be formed intentionally or non-intentionally also. These can happen because we see in our day-to-day life in our lab. Where there is a loop formation, it is the subject of stability. The stability philosophies, those which were established for linear systems like gain and phase margins, are well and good. They make the system stable. They guide us in designing the proper control system. Stability. Anyways, as we have spoken about a system which has got transient response and steady state response, Stability can be defined with respect to this and with respect to this. The standard definitions are, for example, if a system is disturbed, it is disturbed from its equilibrium position. Its states are away from equilibrium position. If the system is coming back to equilibrium, then we call it as asymptotically stable system. That means if here we are talking about only state of the system, not about the input. And for bounded input, bounded output stability, we are keeping the state 0 and checking the stability of system with respect to input. If the input is bounded, for a given bounded input, if the output is, then if we go back to our differential equations here and here, both say the same thing. If it is a bounded system, this is some scaled value or things like that. We have a finite value. Both the state and the input response is dependent on the parameter of the system. If the roots, the roots of this auxiliary polynomial that comes out of this differential equation have got positive real parts, these transients will never die and the system is not a stable system. For a linear system, both bounded input, bounded output stability and asymptotic stability state that the poles of the system, the roots of the differential equations have to be on the left half of S plane. S is a complex plane, which you already know. We express it in sigma plus j omega, the real part and the imaginary parts. Straight away, small example. If a person is doing C language, he has done something y equal to k into y, previous y, a simple. This has formed a loop basically. It is, the function is depending on itself. The function, this is a basic C language example. Suppose if the value of k were less than 1 magnitude wise, this would be a stable system. If it is disturbed from its disturbed to a non-zero state, it will come back upon progressive multiplications by less than 1. It is brought down to 0. That's how stability works here. And if the value of the k is greater than, imagine this goes out of bound. What if k is 1? The value of whatever the disturbed value apart from 0, if non-zero value, keeps on oscillating. We call this system an oscillatory system. In linear philosophy, marginally stable system, because the poles are on the j omega axis of the S plane, and according to Lyapunov, that too is a stable system. A small exercise that gives you a feel of what control engineers do, whether it is a missile, it is a cycle, bike, or any automotive, or any system like that, any biomedical system also. All are governed by the differential equation, basically dynamics, which I am saying, mathematical modeling of the governing dynamics of the system. Let's have a system like this, where tau is a positive real number. This shows that the system is unstable. And only thing that is in our hand is x of t. This is forcing function. We can write a control law. If you have a sensor that senses the output of the system and place the control law like this, when we place it in a closed loop system, we have 1 over the system. We have stabilized the unstable system in this way. This is a fashion. All that we needed was a sensor and a gain. Sensor to sense the output of the system, and a gain over that gives our desired response, and we have placed it, and we have a desired pole in here. This is the way control system design happens, which I had shown you in the first, a closed loop negative feedback system. Little more on that, same thing, same problem statement, little more on. Measure y and place y means we have a sensor that measures y and place a gain on that is stabilizing the system. And if we have further control, we can place a reference input in here. If now the system is made to follow this reference input, unlike the previous system, now it is a tracking system. That means we have stabilized the system and we have designed a control for the system for it to behave in the way we like it. And the same philosophy, similar philosophy goes with our second order system. For example, we have a second order system and we have a negative coefficient which shows that one of the poles is on the right half of the S plane. Of course, this is an unstable system. If we have a sensor that senses dy by dt, I can have a control over the system that I sense it and supply some other gain so that the closed loop system is stable. And it is just I am recalling or making you remember, just recalling the things which what we have studied. This in a second order system, this stands for damping term, while this stands for the stiffness term. This stands for the stiffness term. This stands for the damping term. Stiffness shows the natural frequency or gives the natural frequency of the system. And little more adding to that. Step by step, just I wanted to make you have a feel of all these things. I can stabilize the system, and if I measure the out, earlier we had a sensor that measures the dy by dt, and we have a mechanism to stabilize this part of it. And we can have, if we have a sensors for this, we have the control over the stiffness of the system also. Hence we can have the system stiffness as per our requirement, and damping, we can design the system in the closed loop with damping as per our requirement. Only confidence we have got is we have a controllable system. That means we have a forcing function that can do these jobs. We have
చూడు నాకు వస్తుంది చూడు.
now so this here ends the very basic of a control system. That means we have a control system which may be stable, unstable, or response times are not meeting. To stabilize the system, we have to bring the poles on the right half of the S plane to left half and place them in a particular fashion as governed by our root locus, which we had studied in our BE level. That is the limit for a given closed loop control system, and check whether our whether response times and the stabilities are met. Once the response times and stabilities are met, now the design what we had done is perfect. Having completed those basics, now I am taking into the missile parlance. Missile is just an aerospace vehicle. It is an aerospace vehicle meant for delivering an object from point A to point B, from launch point to target point. And depending on starting from the inception of aerospace industry in 1906, the First World War, the Second World War, the phases of guidance, phases of missiles have changed much. At that point of time, what technology was available, they had given these definitions as per those technologies. For example, guided missile, very old definition. The guided missile is one that is approximately fired in the direction of the target, and there are some ground stations that guide the missile to go towards the target. Nowadays, the missiles are this kind of things. That means missile can change its flight paths. It can see the target with the passengers in itself. That means the organs it is carrying with them in itself, it is able to control by itself. This is the way we are controlling. This is anyways, these both definitions work, and DRDO is on both kinds of missiles like this. And going into the next step, when we are talking about missile, aircraft, a spacecraft, or things like that, this is an aerospace industry. The story goes like this. It is story of four brothers. Like four brothers have structures, propulsion, aerodynamics, and control. Structure, the housing, the civil structure. Our houses our home, which we are residing, are civil. It is just a house with load carrying pillars has load carrying members and things like that. Similarly, an aircraft, a commercial aircraft, and the missiles will have the pillars. They call in a particular terms, in particular terminology, in aerospace structures. I'm not going deep into them. We need to have a housing. That housing is done by structural engineers. Next, we have a structure, but it has to be moved from point A to point B. It has zero speed. So here comes the propulsion person. They design the propulsion system. That means as fuel, petrol, diesel, or CNG we have got for automotive structure, automotive domain, we have specific propulsion systems for missiles. That means boosters, sustainers. Boosters are the propulsion devices that take missiles from zero velocity to higher velocity in lesser time, while the sustainers maintain the velocity, just cancel out the drag that is brought in by the speed of the missile to maintain the velocity for longer time, so that it persists, it has got a good time of flight. And here there comes, after that there comes aerodynamics. Aerodynamics is shape the missile such that the drag is lesser. When we move our hand in air, it, as we go on increasing the speed, we feel drag is the force that is obstructing our motion and preventing our forward motion. And it is akin to when we are riding a bike or car. When we are riding a bike, first gear, second gear, and third gear, that part of the system is booster. While if we want to maintain a particular speed on the road, we have to supply an accelerator. That accelerator just balances the drag that is brought in by the friction between the tires and the road. Similarly, sustainer is the person that just balances the drag and maintains the velocity. Aerodynamicists are the people design airframe with proper aerodynamic shaping so that we can have good lift. There are some terms like lift, drag, and moments. I will introduce them to you, and they do the proper aerodynamic shaping. After all these three brothers are done, here comes our role as electronics and communication engineer. We control all those things. For controlling all those things, we have to know the dynamics of them. We extract the dynamics by proper mathematical modeling of them, and specify we specify befitting sensors, befitting actuators for the closed loop control system design. And to bring everyone on same page, control is nothing but a control system is nothing but a communication system in a given loop. Here the constraint is loop. As the constraint is loop, this is the subject of stability. Based on the mission, the missiles are categorized into surface to surface missile. Basically, the strategic missiles are surface to surface. Because of which we can have strategic advantage over other countries, like 5 years strategic advantage, 10 years strategic advantage. They look into that kind of things. Surface to air, madam. Surface to air missiles. Surface to air missiles are offensive category. We go into particular territory. No. Surface to air missiles are defensive category. If something, some aircraft are coming into our airspace as area defense, we do surface to air missiles. Air to surface missiles are mostly offensive. That means we go to some other's territory and damage their resources. Air to air missiles, both offensive and defensive structures. When we fly an aircraft, and aircraft is being followed by another aircraft, in order to come out of that, we use air to air missiles. In the domain I am working, the missile flight control system. In the missile flight control system, These 4 terms are very important. Not going into full definitions of them, I am just taking you through flight path planning. As I have already mentioned, missile is an aerospace vehicle, goes from point A to point B. Point A is the launch point and point B is the target point. Based on what we are optimizing, we can optimize the energy of the system, we optimize the resources of the system. We have to design flight path from launch point to target point. It is the trajectory. Flight path is the reference trajectory. In a normal sense, reference trajectory, it can be designed before the flight or within the flight, they can be designed. Navigation is the one which tells us whether where is the vehicle, the position of the vehicle and what speed it is going. This is an important term because this is the sensor part of the missile system. This goes to be the sensors part of the missile feedback control. The guidance is a upper level of the control system for a missile, the outer level of control system that controls that maintains the trajectory as governed by the flight path planning. We have a flight path planned already, and how to execute that flight path by kinematic variables like acceleration, velocity, or position. The guidance does all those things. When it comes to control, this is the basic control system, the innermost control system, which actually deals with the dynamics of the system. As governed, guidance wants certain velocity and certain position to be corrected. But how does that happen? It happens when a control loop called autopilot rotates the system, rotates the missile with respect to its relative velocity vector, so that some force is generated, some moment is generated that corrects and that meets the demands of the guidance system. This is the way things happen. A picture, normal picture I am showing general phases of guidance and what control do. First thing is, let us take, if it were a static target or things like that, we have designed a trajectory first. That comes as flight path planning, and there is a guidance. Sir, somebody has a question, or may I continue?
Yeah, continue, sir. Continue.
Sir.
We have a planned flight path, and the guidance system is a closed loop control system per se. It corrects the velocity and position so that the trajectory is maintained. This velocity and positions are kinematic variables. They do not worry about anything. But when it comes to an autopilot, control is an autopilot that stabilizes and controls the airframe with respect to center of gravity. That is the person actually does the motion of missile with respect to velocity vector, so that those forces are attained from aerodynamics and the trajectory correction is done. Roughly phases of guidance would be push phase. This is a smaller exists such that it safely comes out of launch platform. Here I am showing a ship. This launch platform could be an aircraft, a helicopter kind of aircraft, or an airplane kind of an aircraft. So there would be a maneuver with which the missile comes out such that there is no damage to the launch platform. This part of the trajectory is like that. After that, there is a mid-course guidance. Mid-course guidance philosophies are mostly inertial guidance philosophies based on inertial navigation system, lat-long locations and things like that. Based on those, the missile goes from this point to roughly close by to the target. Now from here, there is an instrument or a device on missile called seeker. Seeker actually sees the target. It might be optical, it might be infrared radiation, it might be a radar seeker and things like that. Actual seeker sees the target, and the guidance philosophy changes from mid-course to terminal guidance, where the missile is guided by the seeker, not by the INS. This is how actual missile system works. A guided missile system works. Our thrust area is autopilot design. I'm an autopilot designer myself. Before going into that, a missile looks like this, with center of gravity of as origin, and x-axis is drawn towards the nose, y-axis is drawn towards right side, and z-axis is drawn downwards. This body frame, missile body frame, wherein the vertical plane means x-axis pitch plane. The missile or aircraft does nose down motion, that is called pitch motion. And if the missile or aircraft does right side or left side motion, is called yaw. But if the missile is rotating about x-axis, that means this fin is coming down and reaching here, this control fin is coming down and reaching here, that is a roll motion. Accordingly, so these are the three kinds of motions that are three kinds means there are 6 kinds of motion. I'm boiling them down to 3 kinds of motion. Since there are 3 kinds of motion that are happening with respect to center of gravity, there would be 3 autopilots: pitch autopilot, yaw autopilot, and roll autopilot. Then what is an autopilot? Autopilot is just a closed loop. As I have already shown you the closed loop feedback control philosophy, it is a closed loop feedback control system that is meant for stabilizing this airframe and controlling the airframe as per the guidance requirements. So whatever that happens, because whatever that happens in any non-point mass or non-ball kind of geometries is with respect to center of gravity. Everything happens with respect to center of gravity. Hence, we have to stabilize with respect to center of gravity and control it. As I have told you, autopilot is an inner loop control system, while guidance is an outer loop control system. If we see, there are n number of control systems at various levels. This autopilot is a control system, guidance is a control system. A mission that comes over, there is a mission loop that comes over all these systems, that is also a control system. An actuator, when we see an actuator, it is a position of fins, which in aerospace domain we call them control surfaces, because these are the with which the system is controlled. Because of motion of these things, the system is controlled. How is it controlled? How aerodynamic? How are the effects of aerodynamics come into play? I will explain you in the next slides. Take it for granted that these fins rotating about a hinge line will control the motion of missile about the center of gravity. And as I have already introduced you small differential equations wherein x of t is a forcing function that is controlling the vehicle. So here that x of t is the deflection of these control surfaces. That simple it is. These control surfaces are to be driven by proper pitch control law, yaw control law, and roll control law. Only then the missile would execute what it is expected to execute. A small aerodynamics, because we are electronics and communication people, mostly not aware of mechanical things around us, just a small feeling, so that you can appreciate. In the missile field, as I am working in, missile or any aerospace structure, if the missile is moving fast or the air is or a missile is stationary or air is blowing onto it, it is the same. The aerodynamics, the dynamics performed by the moving fluid on the structure is called aerodynamics. If it is the fluid is air, it is aerodynamics. If the fluid were water, it is hydrodynamics, and so on. And the main important thing is, when the vehicle is going from 0 velocity to this particular velocity, it will have a relative velocity vector. In our case, it is the relative wind that is coming. When we are going with a certain speed, that means the wind is blowing with the particular speed ATAS. So if we have missile properly oriented into the wind, then nothing is going to happen. It is not causing any side force. For the missile to fly up or down, we need to have an angle between resultant velocity, relative wind, resultant velocity of missile or relative wind. We have to maintain an angle with that wind. Only then we can get certain amount of lift that pushes the vehicle upward, so that gravity is overcome and we could see a flight. What is this angle called? This angle is called angle of attack or alpha. This is the angle of attack. When the structure is maintaining an angle with relative wind, it will have two kinds of forces. A force that will take it back, that is called drag. A force that will take it up, that is lift. If the lift force is greater than weight of the system, that mass and mg, mass and acceleration due to gravity, then the vehicle starts flying upward. Same philosophy. As we are talking about pitch plane, the elevation plane, if the alpha is positive like this, vehicle goes up. If the alpha is negative, that means relative wind is upward, vehicle goes down. Similar philosophy, if the vehicle is in horizontal plane, if we want to go to right side, we have to have an angle on the left side of the vehicle such that the vehicle is pushed to the right. That angle in azimuth or yaw plane is called beta, while in elevation it is called alpha. In just a terminology change, in yaw plane it is called beta or side slip angle. In both the cases, it is the angle made by the vehicle with relative wind. So as we have seen, just by changing the posture of the vehicle, with respect to velocity, we are able to change the trajectory of the system. Now, we are able to change. This is how our control system, design flight control system works. And before going to further things, any rigid body has got 6 degrees of freedom. If I take you here, this is a rigid body. It has got axis X, Y, and Z. In aerodynamic sense, aerodynamic or any other sense, it has got 6 degrees of freedom, 3 translational motions. That means it can move along X, it can move along Y, it can move along Z. These are 3 translational degrees. Rotate about X, rotate about Y, rotate about Z. That means 3 rotational motions. These 3 rotational motions are referred to as 6 degrees of freedom of a given system. Since there are 6 degrees of freedom, obviously we will have 6 differential equations, simultaneous differential equations running. This is called 6 degrees of freedom. And based in some amount of aerodynamics, as I have already introduced, people use tail control surfaces and wing surfaces either for control. Here he has used it for when C is placed, it is for control and lift. Mostly these wing surfaces are used for lift. Tail control surfaces and canard control surfaces. The canard control surfaces are used for the control of the missile. If the missile CG is somewhere here, if the missile CG is somewhere here, if the control surfaces are towards the nose side, they are called canards. And if they are towards the tail side, they are tail control surfaces. Both control surfaces do the same thing. They deflection of which control the missile. So how do we control the missile? As I have told you, this missile making an angle with the velocity vector is having a force and moment about force along Z and moment about Y. Similarly, when we deflect these servo mechanisms that are connected to these control surfaces, they deflect them by an angle. That angle in turn makes an angle with local relative wind. That gives us some side force, like we are opening a door. that gives us some side force, and there is a momentum from here to center of gravity. As there is a side force here, there is a moment about center of gravity. So as there is a moment, as we are applying a torque just by deflecting smaller control surface, smaller force but greater moment, the missile rotates. And by rotation of missile, we are going to have a new alpha, a new force, and new trajectory. That's the way the missile control system works. In details of 6 degrees of freedom equations, if we see, there would be 3 translational motions and 3 rotational motions. For every, there are 3 axes: pitch, yaw, and roll. For pitch, 1 force and 1 moment. For yaw, 1 force and 1 moment. For roll, 1 force and 1 moment. So we need to control individually. For pitch has to control pitch force and pitch moment by those control surfaces which I had already shown, by these control surfaces. Similarly, for yaw, we same control surfaces we use in yaw mode, and same control surfaces we use in roll mode for roll control. And these 3 control surfaces we share among pitch, yaw, and roll. Pitch, yaw, and roll, the 3 plants are controlled simultaneously on all these axes, along and about these axes. Now, some more feel of, if the missile has to go up, for example, if the missile has to go up, I need to give a control surface deflection like this. It has to give a force downward, so that with respect to center of gravity, the torque is this direction. As most, there is a moment applied about y-axis. There is a moment about applied about y-axis that causes an angular acceleration resulting in angular rate resulting in angle over time, causing an alpha. That alpha results in an acceleration. Hence, the missile moves. So, missile cannot translate just like that. For the missile to go in a particular direction, it has to rotate and translate. The complexity of the system, I need some feedback, sir, whether it is audible and clear to you, and the slides are clear to you.
Audible and clear, sir. Proceed.
That's it. So there happens, first there has to be rotational motion entailed by translational motion. So here comes the crux. So any autopilot that is stabilizing the missile system has to control that rotational motion and in turn the translational motion. Based on that, for example, missiles have got pitch, yaw, and roll autopilots. Roll autopilot about x-axis, if the missile is rotating and that is to be controlled, is done by roll autopilot. There are roll attitude control autopilots, roll rate control autopilots, depending on their application. And this is about roll. And pitch, yaw. Pitch, that means vertical motion. Yaw, that is horizontal motion. Self to the missile are called lateral motions. There are lateral autopilots. In that lateral autopilots, we do have attitude autopilot and lateral acceleration control autopilot. I will take you through what these things are. Attitude is just an angle made by the missile with the reference navigation system. Sometimes we need to, the translation is secondary. We have to maintain particular angle of the missile. For example, as I have already told you, here there is a launch platform and missile has to come out with particular angle. It should not touch any part of the launch platform. Launch platform, as I have mentioned you, it can be ship or an aircraft also. So it should not jeopardize the platform it is coming out. In that particular initial scenarios, we use attitude control autopilot. Lateral attitude control autopilot. And the other parts, like I have to manage the trajectory. Then comes lateral acceleration control autopilot. That means we are controlling the acceleration perpendicular lateral to and pitch axis or yaw axis. Acceleration we are controlling by proper control deflection given at the tail end by the tail control surfaces, things like that. In turn, it is best just what we generally surface. These are terminologies, and when I take it into the design, these do not matter at all. There are 2 loop autopilots and 3 loop autopilots. for a better control of the autopilot in pitch or yaw plane. I'm taking you to actual autopilot structure. We have pitch, yaw, latex, control, which are yaw, they are identical. Excuse me, I'll have some water and just. As a this is the airframe. Airframe means actuator at the tail end has moved the tail control surfaces. In this pen, these are 4 tail control surfaces. When they move, they cause rotation and translation motion of the whole the vehicle, and those dynamics are captured here in terms of transfer function. When an actuator has given a deflection, the whole missile rotates. So there is a deflection to rotation rate, missile rotation rate transfer function. Similarly, as the missile is rotating, over time there is an angle developed that results in an alpha that causes an acceleration. So from deflection to total missile acceleration, there are transfer functions. In the essence, there is a rotational transfer function and the translational transfer function. Final, our requirement is translational transfer function has to meet the trajectory. But in order to do that in a proper fashion, we need rotational motion. So in a given autopilot, this is a closed loop control system where this is the acceleration command required by the guidance system. Here are the inertial measuring units. In missile, there are 6 inertial measuring units, out of which 3 are body rate gyros. We call them, they measure the body rate in terms of radian per second. In terms of voltage, we convert them into radian per second. There are 3 rate gyros that measure the angular rate of the missile with respect to center of gravity. And there are 3 translational accelerometers that measure acceleration of the missile along X, Y, and Z. Since we are talking about pitch plane, I have placed this Q is called pitch rate and FZ is called pitch acceleration. And this is a standard 3-loop structure for a closed loop structure. As I was already mentioning you at the Taylor series end, 1-loop structures do not suffice. Most of the plants, 1-loop structures do not suffice the control of the stabilization and control of the system. So we go for multi-loop structure. That means body rate is the fastest thing that happens, that is taken as inner loop, and the lateral acceleration, the translation motion happens little late, that is taken in the outer loop. And whole autopilot design in here means design of KR, KI, and KA. These 3 gains are to be designed by an autopilot designer. When we see into details of the coefficients of these transfer functions, we see that they are aerodynamics dependent, they are structure dependent, and so on. So we choose an operating point, linearize the missile with respect to that operating point. In that linearization, we get these transfer functions. For that operating point, we design KA, KI, KR. And as we know, as we have already seen, this mass changes, inertia, moments of inertia of the missile change on the go. So hence, we have our design pilot in offline, KI, KI are guaranteeing us proper step response with time domain specifications and frequency domain stability requirements like gain and phase margin. They have to meet, and as the missile is flying, as the operating points are changing on the fly, these gains also have to change, and they change and to stabilize and control the plant. Before that, I missed a statement. This body rate, which I am calling it as inner loop, which is innermost loop, that is fastest that anything that happens. This is used for damping. This is used for damping, while the outer loop, lateral acceleration loop, is for control. Whenever I say the damping means stability, this is stabilizing the system, while the outer loop is controlling the system. When we see any 2-loop structure, one has to see there are n number of inner loops and one outer loop. Outer loop, what is the variable that we like to control, we place in outer loop, and inner loop variables are meant for stabilization of the system mostly, and outer loops are meant for control of the system. Having said that, it was about lateral acceleration control autopilot. When it is an attitude control autopilot, in some cases wherever it is required, the body, anyways, this loop structure remains the same. Body rate forms body rate loop, the inner loop, two loops are body rate loops. They stabilize the system, and the outer loop, the integration is the angle of the system that has to be controlled. In the essence, multiple loop systems, the inner loops are meant for stabilizing the system, while the outer loop is meant, that means proper response times. Stabilizing, pulling the right half S-plane poles to left half. We have seen these two differential equations, the transfer functions. The roots of the denominator polynomial give us the stability of the system. If they are on the right half, the system is unstable. That means missile, when disturbed, it will go in one direction and will never come back. And we have to employ actuator with proper torque and proper bandwidth, such that although it is an unstable system, it has to be damped and brought back with the control power we have got. And while designing the missile itself, the control surfaces, like aerodynamic control surfaces, which I had already shown in here, the aerodynamic control surfaces which are affected by the aerodynamics are sized such that the moment and the power it delivers is more than the disturbance power in any condition. Only then we can win over the disturbances and take the missile on the expected path or trajectory. Here is about attitude control autopilot. Just a glimpse of Bode plot. Just a glimpse of Bode plot I am giving. When we see the Bode plot, when the actuator, when it is loop is opened here, we see the Bode plot like this. The magnitude response and the phase response. As we know, it is for a stable system. This is for a stable airframe. The Bode plot looks like this. When the gain crossover is wherever there is a gain crossover, this is called gain crossover frequency. We have a phase 44 degrees from 180 degrees. That means phase mark. When there is, we have a gain margin. This happens. This is well and good system. But for an unstable system, something peculiar happens. I did not copy that unstable system wala thing. Okay, I missed it out. Okay, orally I'll explain. For an unstable system, phase crossover happens here also. That means if we reduce the gain, that system is going to be unstable. That system is going to. I'm sorry, really, I did not put the other part of the Bode plot. Okay, to make you have a feel of, we will have a phase crossover here itself. Phase crossover. That means if the gain is coming down, then it is going unstable. That means we can, if the gain is reduced, system is going to be unstable. If the gain is more, system is going to be unstable from the stable part. So there is a bracket of gains. We cannot have gains as high as possible or as low as possible. There is a bracket. In that we have to choose the gains properly. And in the missile terminology, in missile philosophy, since we are using the tail control surfaces, there is a phenomenon called non-minimum phase zero effect. In order to pull this missile up, I have to deflect the surface down like this. Control surface is deflected like this. Air flows like this, causes the acceleration first in this direction. Vehicle rotates in upward direction, and then major acceleration happens towards the upward direction. That means first, because of this non-minimum phase zero, that transfer function that happens to be on the right half of S-plane. This does not disturb the stability of the vehicle, but it causes certain unusual phenomenon called, if we want an acceleration on one direction, initially the acceleration goes in a different direction. Now, since pitch and yaw autopilots are already talked about, there is a roll autopilot. Roll, we use roll angle stabilized missile. Roll angle stabilized missile. So roll angle, we want the missile to be roll angle 0. In order to control roll angle better, we keep roll rate loop innermost. That means this roll rate loop is meant for stability enhancement or damping, while the outer loop is for stiffness enhancement. So these gains are, when properly designed, when the missile is disturbed in roll, it gets back to its roll orientation back to 0, such that so fast that pitch and yaw autopilots will not get disturbed by this motion. In the final implementation, what we have designed, sir, just as a feedback, are the slides clear and my voice is clear to you?
Yes, sir. Yes, sir. It is clear, sir.
An autopilot is designed for an operating point. So that means K and KP are for particular operating point. And KI, KA and KR are for particular operating points. So as the operating points change, we have something called gain scheduling. As the operating points change, gains also required to be changed. So we make gains as function of aero data, that is on the flight, the nominal aero data, what we get, nominal properties, mass properties, and the progression of these properties, structural properties, propulsion properties, and these tables we carry in the onboard computer of the vessel, and we change the gains on the fly based on the operating condition and control the missile meeting our time responses and stability time domain specifications, frequency domain specifications, and frequency domain stability requirements. This is the story about the control law design for a missile. These are some additional topics like control actuation systems. As I had already shown you, a control surface, this deflects and causes an aerodynamic force to change. That aerodynamic force acting at an arm length from the missile center of gravity will rotate the missile because it is applying a torque. So these control surfaces are aerodynamic in nature. Not necessarily all the actuation systems are aerodynamic in nature. There are thrust nature. That means there are control surfaces that can change the direction of thrust and hence rotate the missile in the way we like. And there are some reaction control systems. I have already completed the autopilot design, the basic control system design of the missile, and some other control elements I am introducing you to, so that when you go to any content in the aerodynamic side, you will get to understand. Thrust vector control, for example, if we go for a strategic missiles like bigger Agni, Prithvi missiles, we have bigger missiles with big booster. Big booster means huge thrust they will carry. So there, in order to maintain the orientation of the vehicle, the nozzle is moved. This philosophy is called thrust vectoring. If the nozzle is moved, that nozzle is called flex nozzle. Apart from that, there are this is a flex nozzle implementation. There are two actuators that can move the nozzle. When the nozzle is moved, you can see when the nozzle is moved, major portion of the nozzle is causing the thrust. That means causing the vehicle to go forward. And apart from that, there is a side force that is causing a moment about center of gravity. Moment means torque about center of gravity, that causes the missile to rotate about the center of gravity. So this is control input. That means, as I have mentioned you, the forcing function in differential equation. Now this is the forcing function. This is a forcing function through which forcing function we have seen in the autopilot. It depends on body rate feedback, the angular rate, and the acceleration or attitude feedback in here. That's the way we control the missile. And there are other techniques, like rather having a nozzle, there are, as aerodynamic control surfaces, there are control surfaces in the flame also. If these control surfaces are deflected about these axes, that also causes side force. For example, I have a force along Z at the tail end, that will cause the missile to nose to go up. If I have a force along Y, that will cause a nose to go leftward. If we are looking into the paper with nose already pointed into the paper, this way, this kind of actuation systems are referred to be thrust vector controls. As opposed to them, there are aerodynamic control surfaces. If they are on the tail end, they call tail control surfaces. If they are on nose end, they are called canards. So missiles can be controlled by either tail surfaces, canards, or thrust vectoring, and things like that. There are some not so usual but used by ISRO, and wherever there are missiles going out of the atmosphere, they are reaction control systems. In order to rotate the missile, since out of the atmosphere there is no aerodynamics, we have to fire these thrusters to have a rotation. If you had seen the movie Gravity, in that lady fires thrusters to change the orientation, you could remember, those are the reaction control surfaces. Similarly, there is another graph that is missing. There are other reaction wheels also. Let me explain you. If there is a satellite or satellite-like structures like that, if they have to rotate, some reaction wheels are rotated in a particular direction in order to rotate, because everything happens in reaction. Newton's third law of motion. For every action, there is an equal and opposite reaction. If there is a motor rotating clockwise here, that could rotate the whole structure in an anti-clockwise direction. But because of law of conservation of momentum, the bigger structure moves slow while the smaller structure can move faster. That's the way. Those are called reaction wheels. Unfortunately, that slide is missing. Reaction wheels. With those things, we can change the orientation of satellites where no aerodynamics is available and not even the thrust is available. Some concepts about guidance of missiles. Guidance I have already told you. Guidance commands for kinematic entities like velocity of the vehicle and position of the vehicle to be corrected. Guidance of the that is a control system which is a loop higher, a level higher than autopilot, which we had termed it as stabilizing and controlling entity of the missile with respect to center of gravity. These definitions of guided missiles I have already introduced you to, and the basics. For example, aircraft to aircraft, a missile has to be fired. There would be some pre-program to ensure the. There is a mid-course guidance based on ground stations are based on inertial navigation system carried by the mid-course guidance, and there is a seeker that takes on the target, and the missile is guided towards the target by the seeker. This part is called homing guidance. Inertial, I'm talking about inertial guidance. Inertial guidance are mostly based on inertial navigation system. There are pre-programmed maneuvers, and mid-course guidance phases come under this category. Suppose there is a surface to surface missile, that means launch point is on the earth and target point is on the earth. In such cases, inertial guidances are the first things to be followed. There are other guidance philosophies like command based guidance. We have a radar, it knows where the missile is, where the target is. It will translate these things to the missile so that missile corrects and comes onto the line of sight. Eventually it hits the target. This is command to line of sight. The missile is commanded to come onto the line of sight between ground station and the target so that it could hit the target. And the same thing with little lesser logics. Missile is fired and it has got some entity, some control system at the back end that adjusts itself to the center of the beam of the radar, such to keep the missile always in the center so that it can go and eventually hit the target. These are certain kinds of philosophies. When we go into the guidance philosophies broadly, there are two kinds of philosophies. One is pursuit guidance and the other pursuit guidance and guidance. Pursuit guidance. Pursuit guidance is like this. Always missile is trying to point at the target. It so happens that we have gone so close and the target maneuvered, and missile has no capability of maneuvering. That means it cannot maneuver that fast. For example, such situation can arise and will miss the target as it is. So pursuit guidance philosophies have got such kind of setbacks, while the proportional navigation is another philosophy. It can be made clear in this slide. Proportional guidance philosophy is, we have a target here, we have a missile here. Instead missile looking at the target, it is looking elsewhere in futuristic point so that it could hit the target. This is a famous triangle in this parlance, in the domain I am working, called collision triangle. For example, if we draw a line from missile to target and call it a line of sight angle. If the line of sight angle is not changing, if we make the missile motion, that line of sight angle is not changing and they are coming closer to each other, they eventually hit at a particular point in space. That is guaranteed. That is the whole story of proportional navigation guidance. For that to happen, what should we do? We have a line of sight. Target will have a velocity vector perpendicular to line of sight. Missile will have a velocity vector perpendicular to line of sight. If the missile velocity vector is perfectly matching target velocity vector, this line of sight does not rotate. In other words, for example, it's not met. If the target is moving faster in upward direction than missile, the line of sight will rotate upward like this. If the target is going downward and the missile is not catching up, it will rotate downward like this. If we can match it, that means if we can kill the LOS angular rate, LOS angle is this, LOS line is this, angle made by LOS line with a particular reference frame is called LOS angle. If the LOS angular rate is forced to 0, then the missile is going to force it to 0 means the LOS angle is not going to change and they are approaching each other. There exists a point, they go and intercept it at that particular collision point. Here is the story about the proportional navigation. And nowadays seekers are the systems that see the target. Homing guidance is based on the seekers, these terminal sensors are seekers. Seekers see the target from missile. Residing in the missile, seekers see the target and they calculate the LOS rate. And there exists a guidance law called proportional navigation. That guidance law gives the lateral acceleration to autopilot so that the LOS rate is killed. LOS rate gets killed when the velocity component perpendicular to LOS is matched to that of target. So it is a simple philosophy. Seeker will give a LOS rate and we make the missile to perform achieve the lateral acceleration such that the trajectory adjusted such that the LOS rate is killed. In the essence, we are pushing the missile to be on this collision course throughout at a particular event so that eventually it goes and hits the target. This is the way the homing guidance works. And based on the principle of homing guidance, there are categorizations like semi-active, active guidance, and active homing guidance and passive homing guidance. Here we see a scenario, semi-active. There is a homing head in the missile which is called seeker, but it is not radiating anything. There is a ground center that has radiated a signal and reflected back by the incoming target. reflected back by the target, and these reflections are perceived by the missile, and hence the missile goes on to the target. Since it is not illuminating the target, this is called semi-active homing. With the same understanding, there are radar seekers. That means we place a small radar in the missile. It radiates the electromagnetic energy to be reflected back by the target. That means we know the existence of target there, and LOS angular rates are computed by the seeker, and the missile makes the trajectory that LOS rates are killed to zero. That means it is placed on this collision triangle. Eventually it goes and hits the target. These are two parts. And other part is there are passing seekers also, passing homing heads. For example, there is a target. It may be a ship or an aircraft. It has got an engine. An engine has got heat. There are heat-seeking seekers. That means we are not expending any energy. We are just taking the energy, whatever that is coming, free of cost, and going towards that target. This is called passive homing. In this also, proportional navigation is employed for it to make an interception. So various levels of control systems we have seen up till now in the missile industry, and we design all these things and test them in a simulation environment called 6DOF trajectory simulation environment. That means in that 6DOF trajectory simulation environment, we have to model missile and its subsystems like this with proper mathematical basis. So a mathematical model does that. A simulation, we run those mathematical models, check whether our designs are okay or not. If not okay, we go redesign and design compensators and things like that. This is the way we perfect our control systems design and go for flight tests in the field and evaluate the responses of performance of our designed control systems. Here I stop. This is whole about the missile control system design and things like that. Thank you. Should there be any questions, I am here to take. Thank you.
Any questions from our participants? Okay. Good evening, everyone. On behalf of all participants, I take this opportunity to sincerely thank our esteemed resource person from DRDO for today's enlightening session. The way you explained the fundamentals of missile control system, starting from the basics and gradually moving into advanced concepts was very clear, sir, and insightful. Your examples and real world applications helped us to connect theory with practice. The session was delivered in a very systematic and engaging manner, making a complex subject like missile guidance and control easier to understand. So it has broadened our understanding of aerospace systems and control technologies, which will definitely uh, help us in our teaching, learning, and future research work. We are grateful to DRDO and to you, sir, personally for sharing your expertise with us. We look forward to having more such sessions and collaborations in the future. So once again, thank you, sir, for your valuable time and contribution to this FDP. We truly appreciate it, sir. So thank you very much, sir.
Thank you,
Okay.
madam. It's my privilege. Thanks for the
Yes.
opportunity.
Yeah, dear participants, thank you for your patience and immediately start session 2 as per the link shared in the WhatsApp group. Please. Okay, thank you, everyone. Any doubts from the participants? You can ask. Sir is waiting still. You can ask any doubts related to the control systems and missile guidance. Okay. Okay, sir. Thank you, sir.
Right, well, thank you.